spacecraft.
Telecommunication satellites are an integral part of the modern world. They allow us to send television pictures and communicate over vast distances using all of today's modern technology. But because they operate in deep space, they have to incorporate some extremely complex engineering. A modern communication satellite needs to be capable of surviving the possible impact of debris travelling at thousands of meters per second. And they need to be able to operate in temperatures that fluctuate between -200 degrees centigrade to a blistering 150 degrees centigrade. And yet, the satellite has to continuously operate for a guaranteed 15 years. Because out in space, there's absolutely no prospect of repair.
Oh, you know, I think people do take it for granted. It's like if you pick up your mobile phone and make a phone call, you don't realise it's bouncing off a satellite, or you turn on your TV. It's just like stuff that you do every day without thinking about it.
It's the upper quadrant, section 5.
Yep.
You'll find.
A modern telecommunications satellite can be over 5 meters high and 3 meters wide. Although astonishingly complicated, there are basically two distinct parts forming its main body: the mechanics and the electronics. The mechanics make up what's called the service module, and the electronics make up the communications module. The satellite's central skeleton is built around a carbon fibre cylinder connected to aluminium panels, which hold 4 fuel tanks, a main engine, thrusters and batteries. This is the service module. On top of it sits the communications module, which carries the satellite's complex electronic payload. Also added are solar arrays. Attached to the main body, they capture sunlight, which is converted into electric power, and antenna dishes that will transmit and receive signals from Earth. And by looking at different stages of the build, it's possible to understand how they're put together.
From the manufacturing viewpoint, this is the beginning of the process.
The build begins with a central core, the skeleton of the satellite. Strands of carbon fibre coated with resin are wound into a complex pattern to make the cylinder as strong and light as possible. When it's finished and vertical, it weighs just 20 kilograms and is ready for the next stage of construction.
In here is where we produce our panels, our honeycomb panels. Aluminium skins, very, very thin skins, very lightweight. Low mass is key in terms of space, and we use aluminium because it's good structurally.
The aluminium panels are attached to the central cylinder, forming more of the basic structure. John Richards has been building these for almost his whole working life.
We're just putting the flight bolts into the SM floor, and that attaches the floors to the central structure. I'm not sure how many bolts, probably about 20 in each quadrant. I don't suppose really people just think of satellites as something that are up in space, orbiting round. I don't suppose they think of actually what goes into building them.
You take your time because, I mean, as you're probably aware, these things are worth a hell of a lot of money, and it only takes us to make one slight mistake that could end up costing millions of pounds at the end of the day. Best thing about working here is the people like John and other people that have been here many years, always willing to pass on their experience and to help you out.
After the basic structure is finished, the rest of the systems can be added.
Once I've gone through my final testing, we have a big clean down, make sure it's particle-free, ready to be accepted in the mix area. And I'll give them a shout, and usually that's it. I mean, it's very casual, it's just when you're going to be ready, tomorrow, whatever, and just hand it over to him.
Satellites have to be built in extremely clean environments, because any dirt inside the moving parts can have devastating effects once they're in space. In fact, there are special areas of the factory that actually have fewer dust particles than you'd find in a typical hospital operating theatre. And in here, engineer Graham Viney and team leader Mick Atkinson have the tricky task of managing the assembly and integration of the fuel tanks, the pipework and the engines of the service module.
We do get problems now and again, because when it's designed, it's all done on a model, and then when it comes down to us, it is quite a bit different in the real life, putting it together.
And there's certain things that we know we can't do in the design, because it just won't be able to be done on the shop floor. So what we've got here is the overall service module, or the startings of the service module of the telecommunication satellites. What you can see are 2 tanks of an eventual 4-tank propellant system. On the outside, in several locations, we've got 7 smaller thrusters, and we have a main engine, a liquid apogee engine, which is fitted inside the cone.
The service module carries 4 fuel tanks, all placed around the central core. Each fuel tank can withstand an internal pressure equal to being over 200 meters underwater. The fuel is used for the satellite's engines. The main engine fires the satellite out into orbit after it's launched, and then, for the rest of its lifespan, the other 7 pairs of smaller thrusters will keep the satellite in its orbit. The fuel for all of these engines is delivered by one of the most explosive mixtures known to man: nitrogen tetroxide and monomethyl hydrazine, or NTO and MMH.
As you can guess from the names, these aren't particularly pleasant liquids, so extremely toxic and extremely hazardous. If you take in any of the NTO or the MMH, basically you will suffer from burns, internal burning, and then eventually it leads to death. They are lethal.
The reason for choosing these dangerous fuels is simple: their explosive quality. The more explosive the mixture, the bigger the thrust, and the less fuel you need. But at 3 tons, this volatile mixture is still half the satellite's launch weight. And with such an explosive power, the tanks need to be tested to destruction to ensure they'll survive the trip into space.
Part of the testing from the propellant tanks is to take it to an actual burst pressure. We don't test it with gas, we tend to test it with water. We increased the pressure and we got up towards 49 bar, and the tank will split.
Although the tanks won't be filled with fuel until just before the launch, it's still delicate work fitting them.
We're just about to install the 3rd propellant tank into the structure. 2 are already installed. This is the 3rd one. It is quite tricky, yeah. And it's worth a lot of money, of course, as well. About the price of a good house, actually, yeah.
The propellant tanks are built from titanium because the metal doesn't react with the fuel in any way. And they are machined to be wafer thin.
We've got to be so careful that no damage occurs during this process, so it's quite delicate. It never goes wrong. It can't go wrong. Yeah, it's quite a big operation in the tasks that we perform, so it's good to get it out of the way. We've got it off to a T now, and hopefully tomorrow we'll be putting the other tank in.
It's the end of a successful day, And so with the tanks fitted, the next stage of the build will be adding the engines.
So when I tell people I work in the space industry, it either sparks conversation and genuine interest, or is a complete conversation killer. The concept of satellites came from Arthur C. Clarke back in 1945. He thought, how can we transmit data from one side of the Earth to the other side of the Earth?
These things will make possible a world in which we can be in instant contact with each other, wherever we may be. Men will no longer commute, they will communicate.
With the launch of Telstar in 1962, transmitting sound and vision across continents and oceans became a reality.
They have acquired the Telstar, and Captain Booth puts his thumb up, and there is the picture direct from Telstar. This is the sort of image and the sort of sound on which, in fact, the future of intercontinental telecommunications via space vehicles is built.
If you threw something at the horizon, it would just fall and drop. If you threw it hard enough, you could probably throw it past the horizon, and where would it drop to? Well, it would continuously drop. And that's what we're talking about when you have enough energy to throw a rock or whatever it is to the horizon, but you throw it hard enough that it then continuously falls. Then you're in orbit.
For a satellite to stay in the same place in the sky, it has to travel at the same rate as the Earth spins, once every 24 hours. This is called geostationary orbit, and it can only be achieved at 35,786 kilometers above the equator. Any closer to the Earth and the satellite orbits too fast. Any further away and it's too slow. And that's why in the UK, all TV dishes point at 29 degrees above the horizon. They are all receiving a signal from one particular satellite that never moves in relation to our homes.
Microwaves won't work around the curvature of the Earth. You need to be able to see the point that you're transmitting to or receiving from.
The satellite receives and transmits signals through large antenna dishes that fold out from its main body. But they're very different from the dishes we see outside our homes. They have carbon fibre skins bonded onto a Kevlar honeycomb core. But there's another, more important difference. They don't have a smooth surface.
The customers will specify a coverage. That coverage will be to maximise access to the population and the service area. So for the one which we're looking at here, which is over Europe, we're looking at the landmass of Europe. So the more we can do to suppress the unwanted power over the sea, the more we can put it where they're going to get their revenue from. What we see in the sort of top right corner is what we're actually doing to the reflector. So we're slowly manipulating the reflector surface very subtly, in tens of millimetres, to actually produce a highly concentrated area over Europe.
Shaping the reflectors in this way focuses the signal better. And this is critical because the power they transmit back to Earth is astonishingly small.
The power that we're transmitting for each channel is equivalent to a 100-watt light bulb. And that 100-watt light bulb is at 22,000 miles away from the surface of the Earth. This is quite amazing technology, really.
The satellite is kept in its correct orbit with a series of different sized engines. But given it weighs around 6 tons, it doesn't need the engines you may think.
If you were to fit this engine to your car, you'd have trouble fitting in the 3 tons of propellant, but you may move it very, very slowly. It's not going to take off, but we're in space, so we can use this engine on a 6-ton satellite and move it through space because there's no friction, so it's relatively easy to do.
Once in geostationary orbit, the smaller thrusters will take over from the main engine to keep the satellite in position.
We have thrusters dotted around so that we can control the attitude of the satellite, to keep the antennas pointed, to keep the data flowing. We've got influences from the Earth, which is not a perfect sphere, so gravity will have an effect, and solar radiation from the sun. We have large solar arrays that will pick up from the solar radiation and slowly change the attitude of the satellite, and we need to fire a thruster to bring it back.
These manoeuvres happen regularly, just to keep the satellite in its correct position. But at the end of its life, these small thrusters will use the last of the fuel to blast it even further away from the Earth and into a graveyard orbit, which will be its final resting place. Whilst all the structural components for the satellite are built in Stevenage, the communications module is built in the company's other UK site at Portsmouth.
Portsmouth's history is well known, of course, for the maritime aspects of Portsmouth, but actually for a long time, maybe associated with that, there's been a capability in defence electronics. More than 50 years this site has been here, and over the last 20 years we've seen this shift from defence electronics to, well, space.
It's here that the electronic components that form the communications module are made and fitted.
I don't think we talk about the space activities very much here. I don't know whether it was because it started off being defence oriented and therefore quite secret, and whether that's sort of part of the culture, but nevertheless people in this area don't normally associate it. Even the ones that live here don't know that we make sophisticated satellites.
Over 12 months, thousands of individual electronic components will be designed, built and fitted to the structure. And their reliability is critical.
Failure in space is not an option. Customers spend $150 million buying a satellite, and if something goes wrong, they are not happy and they don't come back to you again.
This communication module is also known as the payload.
On the spacecraft there are many parts, but essentially it comes down to the payload, the reason for it being there, what it wishes to receive and what it wishes to transmit.
Each satellite is guaranteed by the company to work for at least 15 years. If it doesn't, they don't get paid. So attention to detail is critical.
The main driver for what we do here is reliability. So on the site here we have 3,000 engineers, no service engineers. Once our equipment on the spacecraft goes into service, it has to operate for 15 years without any reduction in its quality of service. During that time it gets hot and cold, so the heat on board the spacecraft makes the electronics grow old. The radiation gives it sunburn, so it has to survive through all those things.
At the heart of the communications module are microelectronic circuits called hybrids. These are computer processors, like silicon chips, but are built for space. The circuits are printed onto gallium arsenide, a semiconductor, and bonded onto a ceramic tile. Then they're connected with gold wire.
I'm placing a 1 thou gold wire onto substrate using a combination of heat, pressure and vibration.
Each satellite is made up of around 20 kilograms of pure gold.
It's 99.9% pure gold. So yeah, it's good stuff. Only the best.
Pure gold is stable, doesn't degrade, and is an excellent conductor of both heat and electricity.
I was only 18 when I first did wire bonding, so I suppose I was quite adaptable to it. Even though I've got quite chubby fingers, I quite like doing delicate work, so I haven't tried embroidery yet though.
Once complete, the chips are incorporated into bigger electronic units.
I've been working on this for the best part of 4 years to actually get it from the stages from the early design right through to actually realising some of the hardware. Decoding commands, so it's a bit like you sort of pick up your telephone and you dial a number. This particular unit, crude way, it's doing the same sort of function.
Then the components are tested again and again and again.
We've got about 8,000 test steps on this particular unit on its own. So end to end, it's probably something like around about 2 to 3 months, I would think. But certainly on the design side, you know, you're very conscious that this actually is going to be up there for 15 years, and that's quite at the fore of your mind, you know, in terms of everything you do. Well, it certainly is in my mind, anyway.
But not all the components inside the satellite rely on modern technology.
I've worked in this building for about 12 years, but I've been engaged on crystal growth for the last 42 years. Morning, Mike. Morning.
A huge problem for satellite communication is interference. This happens when the outgoing signal is confused with the incoming signal. This problem can be prevented by quartz crystals built into devices called resonators.
You can look on the quartz resonator as the beating heart. If the heart stops, the patient dies. And similarly with a satellite, if the quartz crystal stops oscillating, the satellite will die.
Oscillating crystals are used to control all the frequencies the satellite transmits. And the quality of the crystal is critical, because if there's any impurity, they won't work.
This is a block of natural quartz that we purchased from a small company that uses quartz for crystal balls. Probably something like that would set you back somewhere between 10 and 20,000 pounds. Okay, Mike, you bring in the crane.
Because Derek needs to ensure the crystal quality and supply, he originally used purchased crystals to provide seeds from which he grows his own.
What we're trying to do here is to replicate the way natural quartz grows in nature. Natural quartz will grow deep in the Earth's crust. The difference is we're trying to speed up the process so we can complete the growth run in essentially a few months rather than a few thousand years.
Over the next 3 months, under a high temperature and enormous pressure, crystals slowly form in a solution of caustic soda.
We've been producing them for 25 years or so, and so far nobody has beaten them.
Once they're formed, the pure crystals are first sliced, then shaped, and finally polished, until they are little bigger than a contact lens, before being incorporated into the satellite's electronics.
Our crystals are the purest in the world, I can say with absolute certainty.
Once all the electronic sections have been made, they need to undergo a series of tests before being attached to the communications module.
My name's Gary Stankham. I've worked in vibration test and mechanical test at Astrium for 15 years now. I'm just going to do a little bit of taping down to tidy it up, and then we'll be ready. Okay.
This test is to check they will survive the extreme physical impact of the satellite's launch.
What we're doing today is we're going to subject this unit to a sequence of vibration tests to simulate the launch environment when the rocket lifts off, and those 8 minutes which will take it into space. It does get a fair old shake, so today we're going to subject it to a 20G vibration test, 20 times gravity. So anything in there will feel 20 times heavier.
Every electronic component is tested in this way, sometimes to breaking point.
It is a hard test, yeah. It's a thorough test, so it has to be. We have to ensure that everything is going to still be working once the unit gets into space. We do see failures, but not too often.
But it's not just the vibration of the launch that each component has to cope with. There are also massive shock waves. These happen as explosive charges decouple each stage of the rocket. From the solid boosters, the satellite housing and main engine, through to the deployment of the satellite itself.
These are quite substantial shock waves, so they need to be tested for. Okay, and that's the shock test.
Once the electronics have survived all these tests, they can be fitted into the communications module. Ian Kilby started work as a technician over a decade ago, but he's now in charge of ensuring everything is connected correctly.
When I moved up from technician to engineer, at that point you're no longer allowed to fit any equipment to the payloads. I do miss the hands-on side of things. I used to enjoy the challenges that waveguide and coax present to the fitters, and yeah, I do. Sometimes I do wish, on particularly bad days, I wish I was back down here on the tools and could not worry so much about things.
At the moment, the communications module is in 2 pieces, and Ian has a brave attempt at explaining how it all fits together.
Basically, the signal, when it's received from Earth, when the whole satellite's coupled, there'll be an antenna, a receive antenna on the top floor. The signal will come in, it goes through the equipment on the top floor. They amplify it, clean up the signal, get the part of the signal we require. It then travels down through the payload, and there will be some equipments called MPMs which are not installed yet. It travels up through the switch network, goes up through the OMUX. Again, it's amplified again and harmonised a little bit more. Signals cleaned a little bit more again at the OMUX level. And then basically it comes back to the top floor, to a feed horn, to the reflector, and then back to Earth. Ian's idiot guide to a payload.
Modern telecom satellites can now transmit over 300 digital channels simultaneously. But just 20 years ago, they could only cope with 10 analog TV channels. And their speed of transmission, or lack of it, was apparent to everyone.
If you think back to like Terry Wogan's show when he used to have one on BBC One, the very first sort of satellite links where they had London, New York, it was almost painful to watch.
She called me, did she?
I hear you calling me.
Am I speaking to Linda Gray?
Yes.
Well, let's establish that it's not working.
With the amount of lag that you had to wait for the signal to go, or Terry's voice to reach the USA, and then the response time back, it was an eternity. I'm sure people remember that. It just took forever.
When we talk on satellite like this, you know, the miracle of sound, there's just a little second or two delay. So it's not that Barry's hearing has gone. It's a long way to Los Angeles.
But now, with the speed of the processing power and speed of modern satellites, it's barely noticeable. It's, like I say, within a second.
Once all the electronic equipment is fixed, the side panels and the central structure are joined together to form the complete communications module. These are some of the most delicate parts of the satellite. And to safeguard them in the extreme environment of deep space, they need special protection.
My name's Katie Smith. I'm the thermal architect here, and I've been working here for just about 6 years. My job is the thermal design, the build, the test of the spacecraft. Deep space environment's incredibly hostile. It's incredibly cold, minus 270 degrees C, whereas the sun-pointing surface, which could be in the region of 150, if not more. And including on that, you're in a vacuum, so there's no convective environment. You can't reject heat like you would, for example, your cup of tea, when you blow on it, removes the heat, doesn't exist.
And the satellite needs to be able to operate within these massive temperature differences.
If we sent a spacecraft up into space with no insulation, it wouldn't work. You'd have one side with severe damage to the structure because of the sun's influence. You'd have possible panels dropping off. So the distortions caused by the very temperature differences would buckle the structure and destroy it.
And the heat isn't just a problem on the outside of the satellite, because these extremes of temperature could be disastrous for all the onboard electronics inside. They can only operate between a cold minus 10 degrees to a warm 40 degrees. So to keep the internal temperature within this range, the satellite is wrapped in material called Kapton.
Kapton is a high temperature layer. It's very robust. You can use it in an environment from minus 250 degrees C up to a continuous operating temperature of about 290 degrees C. I think the best way of describing it to a home product would be a quality street wrapper. It's difficult to tear, incredibly light. So for a space environment, it's hugely applicable.
But Kapton can't protect the satellite on its own.
What you're actually seeing here is a very thin deposition of aluminium. So here, when you can see the gold outer layer, it's not actually gold. What you're seeing is the vacuum deposited aluminium behind the Kapton, like that, giving it an amber or gold effect.
The aluminium-backed Kapton forms a blanket, insulating the satellite and preventing heat being lost to deep space, while at the same time stopping the sun overheating the electronics inside.
I know it seems kind of counterintuitive because you've got large amounts of energy coming in from the sun, but to balance it out and find a happy medium, you have to block some of the sun, dump some of the heat, and supply some heat internally. It's a really complicated juggling act.
The Kapton blanket is the first line of defence at keeping the satellite at a reasonably constant temperature. But the electronics inside also create their own heat, and this too needs to be dissipated. To do this, some very clever engineering is also incorporated into the two large structural panels on the outside of the service module. Complex matrix of pipes act as massive radiators, dumping heat generated by the electronics and keeping the internal temperature constant.
A heat pipe is a very, very effective method of moving heat from one local region to another. There's no working parts, no electricity required, so power-wise it's good.
But unlike household radiators, these pipes contain ammonia, because it boils and vaporizes at just the right temperature, 33 degrees centigrade.
So what happens is, at one end, in the hot, high power dissipation region, what will be a liquid at that stage evaporates. The vapor then travels up the tube, up the center of the tube, to the cold region, and at this region it condenses, it dumps the heat, and then travels back down to start the whole cycle again in the form of a liquid.
There is one final line of defence, which is also crucial in reflecting heat away from the satellite. And it's all down to this team.
I know it sounds very cheesy, but it's a satisfaction of knowing that you're actually contributing to mankind.
To see that power that comes in with no mirrors on it whatsoever, and then when it goes out, it looks beautiful, all polished up.
Yeah, definitely.
And you know, it's serving a purpose up there to protect the spacecraft. You stand back and look at it and go, wow, look at that.
A thin silver surface of mirrors will reflect the sun's rays away from the satellite, and is its last form of heat defence.
These are 100 microns thick, so they are very thin. It's about as thick as a human hair. We have sheets of 198 mirrors at a time, so they're very fragile.
The glass the mirrors are made of also helps to emit heat away from its core.
Just want to feather that end in. Well, we've put the activator in and we've only got 30 minutes to apply the adhesive, put the mirrors on and get it under vacuum. So it is a bit of a rush. It's 8 hours of prep for 30 minutes of organised chaos. The surface that you can see is 99% silver. It's pure silver. And the back surface, the darker side, is nickel and chrome, it's called nichrome. And that is there purely to stop the silver from oxidising. If you remember, if you can think back to your grandmother's silver dinner service, when it goes black, these will go black, and they don't become reflective. That's it, we're done.
In Portsmouth, Ian Kilby is putting the communications module through its final checks in a special room called an anechoic chamber.
We're firing some microwaves at the payload to see if there are any leaks in any of our coaxial connections. So if you imagine the same signal is inside the payload, it's leaked around and it's coming out of a hole, it could in turn affect the input into the satellite and the output going out. So it could actually blind itself in effect with its own loop of RF signal. It's been quite catastrophic in the past to have EMC leaks because it actually interferes with the transmission that's coming from the comms module back to Earth.
The chamber is designed to block out any radio signals from getting in or out.
It's almost like taking a telephone towards a radio. When you're phoning the radio station, you get that big screaming squeal. In effect, not a screaming squeal, but obviously it has a similar effect on a telecoms payload.
With the final testing complete, it's time to box up the communications module ready for shipping.
It's always a nerve-wracking moment to pick up something of this value. It's all the fruits of our labours over the last few months. Lots of things potentially could go wrong. You know, we're picking it up with a crane, we have a failure with the crane, or something catastrophic could happen. Even when it's turning horizontal into the box, it's always quite a nerve-wracking moment. It's quite a large mass.
After over 2 years of intense and complicated engineering, most of the work that takes place in the UK is done, and the modules are shipped to Toulouse in the south of France.
It's always quite pleasing when you see another delivery going out the door.
It's in this facility where the final assembly happens. It's a complicated and delicate process. First, the service module made in Stevenage and the communications module from Portsmouth will be joined together. Then, the solar arrays are added. Finally, the antenna will be attached. Graham Viney has escorted the service module to Toulouse. But luckily for him, it's his French colleague Pascal Gaudin who's in charge.
This phase is key for Pascal. He's responsible for the integration here. For me, you can probably tell I'm a little more relaxed, but I understand what Pascal's going through, but it's not me. So.
Here, at that point, we have a few millimeters really tolerance. That's all. We are all feeling a bit nervous about this because we have to look at all the proximities between the two structures, and the spacecraft is never the same. So each time there are some surprises. So we have to be very careful about this operation.
After 6 hours careful work, the two British-built modules are successfully coupled, and the main body of the satellite is complete.
Yeah, I think more relaxed. We passed the most critical phase of this operation. Now we still have to fit all together the different interfaces which are on different levels. But so far it's a good a success. Yeah, this coupling is a success.
Completing the satellite in Toulouse will take another 7 months of dedicated work. Although all satellites carry fuel for the engines, they are actually solar powered.
My name is Ludwig Grandl. I am the
manager for the Center of Competence of Astrium Solar Arrays here in Germany.
For the last 40 years, the main centre for solar array production in Europe has been this factory. The satellite will have over 20,000 individual solar cells, each helping to generate the electricity needed to power the electronic systems.
What you can see here, that's a typical solar array for our Eurostar programs. One wing, as we see it here, completed with a mechanism, is around 130 kilograms. Though on a satellite we have 2 of them.
Each array is 20 meters long, and yet their combined total weight is the equivalent of just 3 average-sized men. The arrays are folded against the satellite structure for the launch, but once in space, they gently unfold using a system of springs and wires.
Let me say we are extreme reliable in this way, and we never lost function of one of our solar arrays for whatever reasons.
The solar arrays are dependent on a drive mechanism. This allows them to move and always face the sun. And this machine has been designed and built back in the UK by Bob and his team.
This is one of the key critical elements in the spacecraft, so it has to operate every day for 15 years. If we lose this, we lose power into the spacecraft. That causes the mission failure.
This mechanism is one of the most critical components of the whole satellite. It has to move the solar arrays to face the sun every second of every day for its entire 15-year lifetime. Because if it doesn't, the satellite will lose power.
This provides 2 functions. It provides the power transfer from the arrays, and then it also enables the arrays to track the sun by rotating it 1 cycle per day. This is the spacecraft. These are the arrays. So they sit in here, holding the arrays. And if you imagine my fist as the Earth and the camera perhaps as the sun, then as the Earth rotates and the spacecraft rotates, you'll see that if you don't rotate the array to track the sun, then you don't get the power. So we have to rotate as this spacecraft sits in geostationary orbit above the equator, moving around the Earth. We have to rotate these so they're always facing the sun. There's a very, very high pleasure in engineering, in getting something right. The fact that you can actually see something which was, in effect, something in somebody's imagination turn into reality, and for it then to be successful, is a tremendous kick. It really is.
With everything fitted and tested, the satellite is carefully packed into a high-tech crate and sent by plane to the launch site, where it's prepared for its final journey. It's a tense time for the whole team.
We're in the satellite control centre, and this control centre takes over control of the satellite after it's separated from the launcher. It is critical, it is a crucial phase. Good line pressure to fire the thrusters. At the moment, this team here is running through a rehearsal. There's a computer simulating everything that the satellite does. We can send commands as we would. It responds like a satellite, and it's really testing the team.
As the satellite is being prepared for launch on the other side of the world, these rehearsals are critical, because when it leaves the rocket that gets it into space, its orbit will be elliptical.
The moments leading up to the firing of that main engine is very tense. A lot of pressure. If it doesn't happen, we have a lot of people looking at us.
Graham and his team will then have to fly it into the correct geostationary orbit by remotely operating its main engine and thrusters. Each burn will take up to 90 minutes, But overall, the procedure will take 2 weeks and use half of the available fuel.
Every time we circularise the orbit of a satellite, there's something about those 2 weeks where something will challenge us.
The launch day is fast approaching, and over 4,000 miles from Stevenage, Bob Graham is following the satellite's journey.
We're in French Guiana, which is in South America and very close to the equator. Green, lots of green trees, very, very hot. It's about 37 degrees today. One of the reasons we launch from the equator, or very close to the equator, is that because the Earth spins and there's a faster rotational speed actually on the equator.
It makes business sense to fire a rocket into space from the equator, as it's cheaper to launch.
Which means less fuel, means a lower cost launch, and from the spacecraft's perspective, it's actually being placed closer to its end orbital position. So again, it uses less fuel on the spacecraft.
The satellite will be lifted into orbit by an Ariane 5 rocket. At over 50 metres and almost 800 tonnes fully fueled, this is the workhorse of European space exploration.
Our satellite is right at the top of the launch vehicle. You can see the fairing at the top, the curved part. It's literally sitting right inside there.
Watching the launch has a special resonance for Bob.
I've worked in the space industry for nearly 30 years. Never seen a launch in my whole career. Never. To be so close is a really incredible and moving moment, because a lot of people do not actually get to witness this. I feel terribly privileged that I'm here, and I would see myself as a representative of people who've actually contributed to the delivery and the success of this spacecraft. You're talking about 30 million horsepower at launch. So the thrust when this vehicle takes off is about the equivalent of 12 A380 Airbuses taking off. This is a pretty rough ride for the satellite, and that's what all the design and everything is about. We have to make sure it survives this phase, and then it can go into operation. So it's yes, this is the bit where we all get that little bit of butterflies in the stomach, which is saying, I hope this goes all right. Maybe even some sweaty palms. Let's wait and see.
Later that day, the rocket is carefully rolled out to the launch pad. It's taken over 2 years, in excess of £100 million, and some exceptional engineering to get this far. And now, there's nothing Bob can do, except wait. Launch day, and on schedule, the automatic countdown commences. At first, everything goes smoothly. But at just 1 minute and 47 seconds before ignition, the countdown stops.
The window is now opened and there's now a hold. There's obviously some problem somewhere which they're checking. They're going back to restart the 7-minute countdown. So we will see how it goes from here. That bit of butterflies, is it going to go? Is it going to go? And is it going to be as they say it is, in terms of the light, the noise, and yeah. So let's see.
As night falls, it's apparent that the technical issues are more serious than first thought. And after an hour of waiting, the launch is cancelled. The next morning, An initial investigation suggests a faulty fuel valve in the rocket caused the postponement.
Here we are in Mission Control, Jupiter, the morning after. This is the place where that final decision was made last night to postpone it. As an engineer, I know this is the right decision. The decision made last night was the right one, but as a man, as a person, as a representative of a team, yes, there's an element of disappointment in there that it didn't happen. Space is difficult. It is about risk. It is about showing that our products are good and we can't afford to take the risks. But it will happen again, and maybe I won't see it, but others will, and I guess that's life.
And finally, the satellite was successfully launched. Today, 35,786 kilometers above us, the brand new communications satellite is now being prepared to broadcast pictures directly into your home. So keep watching the skies. From sketch to structure, see how designs come to life by visiting bbc.co.uk/how to build and follow the links to the Open University.